Well, hello everyone. This is Apurva. I'm an AI developer advocate here at MongoDB. And today I'm going to talk to you about a retrieval technique called parent document retrieval. But yeah, before that, just some light housekeeping. Feel free to drop comments in the chat, just talk to others who are tuning into the live stream, drop in where you're tuning in from. That would be the place to ask any questions as we go through the live stream today. So the way this is going to work is I'll be talking about a tutorial that I wrote on this topic for a little bit, and then we'll move to like a live coding session. And I'll keep taking breaks as I go along to see if there's any questions coming in. So yeah, I'll be closely monitoring the chat. And then once we are done with the live coding, we'll have dedicated time for Q&A as well. So we'll be sure to answer all your questions. So yeah, like I mentioned, today I'm going to talk to you about a retrieval technique called parent document retrieval. I wrote a pretty detailed tutorial about this a while ago, and it should be linked in the video description or will be in the future. So feel free to check that out after. But for today, we are going to quickly go through some of the key concepts from the tutorial, and then we'll recreate the code that accompanies this tutorial live. Does that sound good? I certainly hope so. So let's get straight into it, right? Let's first talk about what this technique is, when you'd use it, and why you'd use it. So let's look at this section right here. So when chunking documents for LLM applications, there are often conflicting considerations. I see sorry, got distracted by a comment. I'll come back to that later. When chunking documents for LLM applications, there are often conflicting considerations. You want your chunks to be small enough so that you have good embedding quality, but also you want the chunks to be large enough so that the context that you need to answer a specific question is not spread across multiple chunks. And this is difficult to achieve using a single chunking strategy with a predefined chunk size that one normally does. And this is where this technique called parent document retrieval comes in and really shines. So in this technique, what you do is you store and embed chunks. Let me keep that on, right? So what you do is at storage time, you store and embed small chunks, but at retrieval time, you fetch the source document or larger chunks. And this results in this effect of context expansion at generation time. And some use cases for this technique include documentation chatbots, where a user might ask a question about authenticating to, say, a particular API. And if you want your chatbot to not only specifically answer this question, but provide a more holistic answer and also some peripheral context about, say, token expiration and refresh mechanisms from the same document, then you might consider this technique. So now let's talk about how this works in MongoDB. Just making sure. Oops. Okay, that did not work. Okay, that's much better. Cool. So it's important to understand how this works in MongoDB, even though I'm going to be showing you how to implement this technique using our LangChain integration. But yeah, let's quickly talk about how things work under the hood. So given a document at ingest time, it is split into chunks using whatever chunking strategy you use, and then it's embedded and ingested into a MongoDB collection. But there's an additional detail here, which is each chunk document also has a parent ID field attached to it, indicating the source or parent document that it came from. And finally, the parent documents themselves are ingested as is into the same collection. So the parent documents will have an underscore ID field, which will match the parent ID field in the chunk documents that are generated from this parent document. So then at retrieval time, the user query is embedded and chunks that are most relevant to the query are retrieved using vector search. But it doesn't end there. There's an additional step where we use the $lookup operator, which is part of our aggregation framework. So using that, using the parent ID field in the chunks, we retrieve the parent documents from the collection. And if there's any duplicate documents, so say there's two chunks that came from the same parent document, then we'll do like this deduplication stage to only pass on distinct parent documents onto the LLM to generate a response for the user question. So yeah, that was kind of the quick concepts run through. I'm going to pause at this point to see if there's any questions before proceeding to the live coding part of this live stream. Let's see. So someone says we are doing a project in which we are storing our data set in MongoDB and give it an LLM for RAG implementation. Awesome. So hopefully this technique will be useful for you. So wherever you are with building your RAG application right now, when you say evaluate your retrieval performance, and if you find any gaps there, then this would be one of the advanced techniques to consider to improve that performance. Actually, I think I'm sharing the wrong screen. Okay, that's the one. All right, so I'm going to be coding in a Jupyter notebook for the rest of this live stream. I have created, done some just initial installation of the libraries that I require and set up the prerequisites that I'll require for this coding session. So installing the libraries first. So datasets, this is a library to download datasets from Hugging Face, which is what we are going to use. PyMongo, which is MongoDB's Python driver. LangChain, this consists of like the core functionality of the LangChain framework. And then there's LangChain MongoDB, which is MongoDB's official integration with LangChain. And then there's LangChain OpenAI, because I'm going to be using OpenAI embedding and chat completion models here. And then this is where I set the prerequisites. So I need to set an OpenAI API key. Then, oops, I'm on that. The MongoDB setup, so just entering my MongoDB connection string and making sure that I'm able to connect to my databases and collections in MongoDB. And then finally, a Hugging Face token. So typically you don't require this, but it's required for the specific data set that I'm using in this tutorial, which is our docs data set. And this is a gated data set on Hugging Face, but this is a subset of literally our official technical documentation. So it's a great data set when you're trying to prototype production level apps and get a sense of what data looks like in the real world. And that's important when you're building RAG kind of applications. So yeah, if you want to use this data set, you need to request access. And then if you're trying to programmatically download and access this data set, you also need to set the Hugging Face token in your IDE. Cool. So the next thing I'm going to do is actually go ahead and download the data set. So the data set consists of like 6,000 rows, but for the purpose of this demo, I just want to use top 1,000. So I'm going to load this in streaming mode. So I'm not downloading the full data set to disk and reading from there. All right. Let's quickly preview the data set. Okay, so as you can see, it has the date when this particular documentation article was updated, an object ID, and some metadata around what type of content it is, and any description about the document itself, the source of where the document came from, and the actual body of the document, and the URL and title as well. Cool. So the first thing I'm going to do is convert this data into LangChain documents, and I'll show you what this means in just a bit. Okay, so I'm going to iterate through rows in my data frame, and I'm going to generate the content of the document, which is in the body field. And then I'm going to retain only a subset of all these metadata fields that you see here. So I'm just going to keep the updated date, URL, and title. I'm going to extract that as the metadata for the document. And then finally, I create this LangChain object. So essentially, a LangChain document object. And essentially, a LangChain document it contains the page content, which is the actual body of the document, and the metadata. And this can be any peripheral information that is truly descriptive of that particular piece of information. Go ahead and run that, and let's see what that looks like. Cool. So you see we have, this is a document object. It has a metadata attribute, which consists of the fields that I selected, and finally the page content, which corresponds to the body of the document. Okay, make sure that we did this for my full data set. Yeah, 1,000, that looks good. Let me hop back to see if there's any questions. How efficient is real-time RAG in retrieving the correct data chunks from a database? Are there any specific methods to improve the retrieval speed from the database? Yeah, so if you're talking mainly about speed, actually, there's two parts to this, right? How efficient is real-time RAG in retrieving the correct data? So correct data goes more into the recall of the retrieval process itself. So that's where techniques like parent document retrieval, hybrid search, or like contextual retrieval come in. But because all of these have some additional steps, those are going to add a little bit to the latency of your application. So if you if you want to optimize for accuracy, then you would look into these techniques. But if you want to get like a better trade-off between recall and latency, then you could look into possibly a smaller embedding model, or also quantizing your embedding. So both of these are going to impact the retrieval rate of your application. So if you do that and then use some of these techniques, I think you could achieve a good trade-off between accuracy and latency. Okay, so now I'm going to initialize a text splitter or chunking strategy for the child chunks. So I'm going to use the text embedding 3 small model from OpenAI. And eventually I want my parent and child chunks to end up in MongoDB. So I'm going to set the database and collection name where I want them to end up. And then this helper function that returns a text splitter object for a specified chunk size. So I'm using the strategy called recursive text splitting. Actually, what's it called? It's called recursive token with overlap. So essentially what this does is it first splits up a piece of text based on a list of characters. I believe it's like periods, commas, and spaces. And then it'll try to merge these characters into tokens until the specified chunk size is reached. And then the overlap pieces that you're trying to maintain some level of overlap between going from one chunk to the next. And typically, I try to start with an overlap of 15 to 20% of the chunk size. And all this is to keep like the context continuity at the chunk boundaries. All right, there's that. And then I'm going to instantiate the parent document retriever itself. So we have this class called MongoDB Atlas Parent Document Retriever in our LangChain MongoDB integration. And this is what creates a parent document retrieval object. So if you wanted to get into the details of what this does, just look up this class our in the GitHub repo for our integration library. And then if we use this from connection string method of the class, then it automatically creates an instance of a MongoDB Atlas vector store and document store behind the scenes. And what the vector store does is when documents are added to that interface, it's going to chunk, embed, and ingest those chunks into MongoDB. And then the document store is going to basically put the parent documents as is into MongoDB. So that's why you specify the connection string, basically all the parameters that both those interfaces require. So the connection string, embedding model, which is required by the vector store, child splitter, again, required by the vector store. So here I want to create chunks with a chunk size of 200 tokens, the database and collection name, the text key, which indicates where the raw text of each document resides, like which field or path. And here it's under the page content field. And then search arguments, which specifies, in this case, the case specifies how many documents you want to return from the vector search. Okay, gonna do that. And also, there's another flavor of parent document, which is called parent chunk retriever. So in parent document, at retrieval time, you're retrieving the full source document itself. But what you can do is retrieve larger chunks. So you're still getting the effect of getting more context at retrieval time. But if you find that your parent or source documents are too large, then instead you can break those up into larger chunks and retrieve larger chunks instead. But for this example, I'm going to use the parent document retriever and not the parent chunk. But if you want to do parent chunk, then you would pass an additional parameter to the parent document retriever object, which is the parent splitter, and specify a chunk size for those larger chunks as well. Cool. So now I'm going to add some documents to the parent document retriever. So remember that vector store and document store, they'll ingest those documents into MongoDB behind the scenes, but you still need to add those documents to the parent document retriever. Okay, so here I'm going to asynchronously ingest documents into MongoDB. And this is less important since my data set is pretty small. We are just working with 1,000 documents. But typically in production grade enterprise applications, you're working with potentially large data sets. And this is where like asynchronously processing your data would become more important. So you're not sequentially processing documents, and no tasks are, you can ingest documents in batches and in parallel. So I'm going to say set a batch size to 256 and max concurrency to 4, which means I want to work on 256 documents at a time, and I want to have 4 different processes running in parallel at any given time. I'm going to define a bunch of helper functions first. So this function called process batch, it takes a semaphore. And if you've ever worked with the async IO library, semaphore basically defines the maximum concurrency level for the asynchronous processing. So here, it'll make sure that I'm not using any more than 4 processes at any given time. And then I'm going to add documents to the parent doc retriever object using the add documents method from LangChain. And this is just an asynchronous flavor of the add documents method. And I'm going to pass it a batch of documents to process. Okay. Then this is the function that actually creates the batches. So it's going to take the full list of documents and it's going to iterate through them and yield a subset of documents based on that specified batch size. So it's going to yield 256 documents at a time. And then finally, this is the main function. So you set the semaphore here, you get the document batches, and for each batch, you spin off a task, and you call the process batch function, which is the one that's adding documents to the parent document retriever. And then you wait for the results from all the tasks and basically wait for all the tasks to complete. And that's when you'd say that you've processed all your documents. Cool. And this takes a little while, so I'm not going to run this right now, but just wanted to walk you through what that would look like, and we'll take a look at what the documents look like in MongoDB as well in my collection. So you specify the collection, delete any existing documents, and then you spin off the document processing. So when that goes through, this is what you're going to end up with. So I have this LangChain database with a parent doc collection. So remember, we started with 1,000 documents, and after chunking, we ended up with about 25,000 documents, and this includes the parent documents themselves. So this is what a child document looks like. So you have everything and then the doc ID. And the reason I know this is a child document is because the parent document wouldn't have this field. It would instead just have the underscore ID field. And I also at some point ran a version of the parent chunk retriever. So notice that we end up with way more documents than the parent document retriever, because instead of the source documents also getting chunked into larger chunks. So we almost ended up with 10,000 more documents. But the format of the document still looks the same. Okay, going back to see if there's any more questions. Okay, nothing so far. All right, so then the first thing we are going to do is retrieve chunks using vector search. So let's get set up for that. And what we need in order to perform vector search, the first thing we need to do is to create a vector search index. And you can do this programmatically using the Python driver. So you're going to define the index definition. So essentially, the type would be vector, the path to the embedding field, the number of dimensions, and this would depend on the embedding model you use, the similarity metric. We support cosine, dot product, and Euclidean. And for the person who was asking about how to improve the latency, if you want to do quantization, you would also just say something like quantization true. And this would, and then we would automatically quantize your embeddings behind the scenes for you. And finally, yeah, the name of the index and the type is vector search. So that's the index definition. And then we actually create the index. Like here, we check if the index already exists, and if it doesn't, then we create it. But the way to create the index itself is using this create search index method. Okay, so looks like I already had an index, so it's just going to skip that. All right, so now let's look at how to use this parent document retrieval in the context of a RAG application, and we'll also look at an agentic application using LangGraph. So let's first look at RAG. So I'm going to create a very simple RAG chain using LangChain. So the first step is going to be retrieval. So I'm saying use the parent document retriever, and then piping that with this pre-processing step. So essentially, the documents that are retrieved from the parent document retriever I'm just joining those into separated by two new lines. So just like structuring them into paragraphs. And then the question is just being passed on to the next step. And then the way to do that in LangChain is using this abstraction called runnable pass-through. So this is just going to take an input and pass that along to the next step in the chain. And defining a prompt template, pretty simple here. Answer the question based on the provided context. If no context is provided, respond with I don't know. I find this a very simple, but in most cases, effective technique to introduce some grounding into the LLM responses. So yeah, then using that template to define the prompt, initializing the LLM I want to use. I'm using the latest version of GPT-4o, and then some light parsing on the output from the LLM, which is just to parse the output as a string. And then here's where I'm finally putting the RAG chain together. So first you have the retrieve stage, and the output from that is piped to the prompt. So it's going to fill in the context and question here. That's piped to the LLM, which will generate the responses, and that the generated responses is going to be parsed using this string output parser. So essentially, if I try to invoke that RAG chain, it's going to go through all these steps and provide me the final output. Cool. So I'm asking it a question. How do I resolve alerts in MongoDB? So okay, so let's look at the response. So if you look at this, right, like it's telling you how to fix the immediate problem, but you can see that the response is a little more rounded in the sense that it's giving you potential ideas for how to implement a long-term fix, how to monitor your alerts, and also how to like acknowledge and unacknowledge alerts. So my hunch is that if we didn't do parent document retrieval, then it would be a much more succinct response and just adhere to what exactly the user was asking. But with this technique, you get a more holistic response. Okay, so now let's look at how to use this retrieval strategy in an agentic setup. Anyone building AI agents yet? If you are, drop a yes in the chat and tell me more. Okay, so the it's really easy to convert any Python function or the retriever that we created previously into a tool for an agent to use in LangChain. It's as simple as using this add tool decorator. So you could have virtually any Python function and convert that into a tool for an agent to use using this add tool converter. All you need is the name of the function, the arguments to the function, and a description of what the function does. So here, writing a pretty basic Python function like before, saying it's just going to invoke the parent document retriever and perform that same pre-processing of structuring the output from the retriever into paragraphs, and it's going to return that parse string. Okay, so then we are going to create the list of tools that our agent has access to. Here it's just this one tool, but it could be multiple tools that you give your agent access to. And this is where I'm going to bind or basically tell the LLM that, hey, you have access to these tools. So initializing the LLM, creating the prompt template. So again, two things to note here. Same as before, just telling it if you can't get enough information from the tools that you have access to, just reply with I don't know. And this sometimes prevents the agent from going into these like infinite tool calling loops. So sometimes I've seen the LLM just call the same tool over and over because it doesn't realize that it hasn't gotten it's not going to get the response it's looking for from that tool. Do not rerun tools unless absolutely necessary. Again, helping prevent that infinite tool calling loop. And then think step by step and use tools. So this think step by step is a very easy way to imbibe chain of thought prompting into an LLM. And this is more important for agents because it just helps with their planning and reasoning process. Cool. So now I'm going to partial the tool with the list of tool names. So it's essentially going to fill in this placeholder for tool names and then give the LLM knowledge of the tool. So I'm going to chain the prompt with the LLM with tools by using this bind tools method, which is going to bind the tools to the LLM. Cool. So as I mentioned before, and let me check back for questions. There's one, what type of clusters are best for an LLM RAG application? Dedicated clusters or serverless clusters? So I think dedicated clusters can also be serverless. Are you asking more local versus cloud? Yeah, I'll check back again to see if you can clarify what you mean there. All right, so as I mentioned before, we are going to use LangGraph to create our agent. And the idea here is to structure LLM workflows, not just agentic applications, as graphs. And the graph has three main components. It has the graph state, nodes, and edges. So the state is essentially a central class that has a list of attributes. You can add any attributes to it, and these attributes can be modified by the different nodes in the graph. And then nodes can be basically any Python function which composes the core logic of the agent. So as you can see, this one can be converted into a node if you wish, which is what we'll do. And then edges, which can be fixed, conditional, or cyclic. And these basically determine what the flow of the application looks like. So like which node to start from, which one to end at, and like if there's any loops to be taken from start to finish, things like that is what you define using edges. So state, nodes, edges, the first thing we are going to define is the graph state. So in my graph state, I basically just want to track the messages. So messages from the user, messages from, and messages from the agent. And then we are going to have two nodes here. One is the agent node. So the first thing it's going to do is read messages from the state, and this is where the agent will, this is how the agent will get the user's input, and it's going to invoke the LLM with tools that we defined here with the user messages. And this can also contain any like chat history from the previous messages in the conversation, basically. And then once it has a response, it's going to add that to the graph state. And the response could either be the final answer to the user question, or it could be an intermediate response that says it has identified that it needs to use a tool. And then the messages itself will be like the arguments, basically what tool to use and what arguments to call it with. And the other node we'll have is a tool node. So LangChain has this quick abstraction for tool nodes called, no surprise, tool node. But if you wanted anything custom, then you could just write a Python function to do anything additional that you want in the tool node. And then I'm going to parameterize the graph with the graph state. And then this is where I'm going to first add the nodes. So I have the agent node, the tool node, and then the graph edges. So I want a fixed edge from the special node called start. So basically it's the node which doesn't have any predecessors. So in this case, the first thing we want to do is go to the agent node And then there'll always be a fixed edge from the tool to the agent node, because we want to send feedback from the tools back to the agent always. And then there's going to be a conditional edge from the agent to the end node, which is again a special node and it doesn't have anything after it. So it's saying have a conditional edge from the agent node and check this tools condition. Again, this is a pre-built, but essentially if you look closely at this pre-built method, what it does is it's basically checking if in the agent's response there's a tool call mentioned or not. And if there's a tool call, then based on that condition, we want to go to the tools node. And if there's no mention of tool calls in the agent's response, then we want to end the workflow, because we know that the agent has gotten to the final answer at this point. So then we are going to compile the graph. And now all that's left is to execute the graph with an example input. So again, my input is going to be how to resolve alerts in MongoDB. And I'm going to stream the outputs from the agent. So that way I'm not waiting for the final response to arrive in like a huge block, but I'm just getting the response as the workflow goes through the different nodes of the agent. And then I'm just going to print out which node the execution is at and what the value of the execution or the response is. And then once it has the final answer, I'm going to print the final answer. Okay, so let's do that. Okay. Okay, so let's see what happened here. So first it goes to the agent node, and yeah, so the agent determined that it wants to call a tool, and it's come up with the arguments for the tool and the name of the tool. So the next thing that's going to happen is we are going to actually call the tool. So the tool gets called here, and then you get back the response from the tool, which is the the context retrieved using the parent document retrieval. And then if we scroll all the way here, hang on. Yeah, like at that point, the agent determined that it got to the final answer, and then this is the final answer printed. So even here, as you can see, it gives a more holistic response to how to resolve alerts. So it tells you how to first understand the alert, how to view alerts, and then options to like acknowledge, resolve, unacknowledge, and monitoring future progress. And again, here, I think if we didn't use parent document retrieval, it would be a much shorter response. So yeah, that's essentially what I wanted to show you for today. So I'm going to stop sharing my screen and go back to see if there's any questions. Okay, so going back to that question, which type of clusters are best for LLM or RAG? And you said yes, so I'm going to assume you meant local versus cloud deployments. So typically, we see folks preferring local deployments in sectors like the government sector, financial, legal, healthcare, where the data is really sensitive and there's concerns around different GDPR policies for different uh, countries. So those are the kind of verticals that we see wanting to uh, keep and access their data as in a as secure a way as possible. So those are the ones who prefer local deployments. But even there, we are seeing folks move to cloud clusters just because that way you don't have to worry about maintaining updates, backups, rollbacks if something goes wrong. And that's usually managed by like some cloud vendor, like MongoDB in our case, but we use like AWS, Google Cloud, or Azure. And these vendors usually have more resources and processes in place to do all of that for you so you can actually focus on building applications. Okay, there's another question, how we use dynamic query. Not sure what you mean there, so if you could clarify that a little bit. Yeah, one final resource I wanted to point you out to before I drop is our our Gen AI cookbook. So this has a pretty exhaustive list of all kinds of examples and techniques. So the example that I was just showing you, it's in there. And then there's a ton of examples on RAG and agents. So yeah, go give that a star. Uh, Click the watch button so you know when new examples are being added to that repo. Use of pivot data in dynamic queries. Um, So I don't, there's no concept of pivot data in MongoDB, right? That almost, and again, I'm no database expert, but that almost sounds like an RDB BMS terminology. And MongoDB is a very different way of thinking about data where you don't have a concept of tables. If anything, like collections uh, are parallel to tables, but even with a collection, we are storing documents in a JSON-like schema. So in a document could essentially have the embeddings, any metadata, and any operational data all in the same document. And even like data that looks a little bit different can coexist in the same collection. So I'm not sure what pivot data would mean in the context of MongoDB, but we can just ping me on LinkedIn or something, and we can chat more about what your use case is there. All right. If there's no more questions coming in, I think I'm going to end the stream now. And yeah, like I mentioned, you can catch me on LinkedIn in our community forums. And yeah, I'll see you next time. We do this every week. So yeah, I'm sure I'll see you again. Thanks. Bye.